Hi, this is Sarah, and in this video I will be explaining a few homework questions that we have covered earlier in the year. I'll be discussing Lewis structures and polarity, as well as reactions and their rates. So our first problem, number 116, asks us to write Lewis structures and predict whether each of the following is polar or nonpolar. We're only doing parts D through F, but our compounds are CF2CL2, SCF6, and H2CO, where C is the central atom. Unless stated otherwise, like letter F, the first atom in the compound is usually the central atom. So, let's start with CF2CL2. First, we need to find the total number of valence electrons to know how many electrons we need to draw. You can do this by finding each individual element on the periodic table and counting which column it is in, excluding the transition metals. So C has 4 valence electrons, and F2 and Cl2 have 14 each, totaling 32 valence electrons altogether. Now that we know the total amount, we can begin to draw the Lewis structure. C would be the central atom since it's first, and then we can draw 2 single Fc bonds and 2 single Clc bonds. Each one of these single bonds is technically 2 electrons, so carbon is all set, and we've used 8 of our 32 electrons needed. Since each atom already has 2, we just need to draw 6 electrons around each one. Every atom in this compound must have 8 electrons to be stable, no more and no less. And since we used all of the electrons necessary, CF2CL2 is stable, and now we can determine its polarity. You can do this by looking at a compound symmetry in its molecular shape. CF2CL2 is tetrahedral and would be nonpolar, but because each surrounding atom isn't all the same, it is polar. Next, for part E, we have the compound SEF6 with 48 total valence electrons. Se is the central atom since it's the first molecule in the compound, and it has 6 single SeF bonds because there are 6 total fluorine molecules. Se can be stable with more than 8 electrons, but F still is only stable with 8. We currently have 12 valence electrons out of the 48 needed in SeF6, and since each fluorine atom already has 2 electrons from each single bond, each one just needs 6 more. After drawing those, we now have 48 total valence electrons, which means SeF6 is stable. Now we can determine its polarity as well. SeF6 is octahedral, which is a symmetric molecular shape, and one that has no lone pairs of electrons. Therefore, the compound is nonpolar. Finally, part F, our last Lewis structure problem, is the compound H2CO, which has a total of 12 valence electrons. This one will have 2 single Hc bonds, and H can only be stable with 2 valence electrons, so the single bond is all it needs. C and O also share a bond, but after that, we've only used 6 of the 12 electrons needed. C only has 6 electrons, so we need 1 more pair to make it stable, and O only has 2 electrons, so we need 6 more around that one to make oxygen stable. However, with this compound, because our central atom, carbon, and the atom oxygen both have lone pairs of electrons, we can cancel those out and draw a double bond between C and O, still making H2CO stable. And now for its polarity, H2CO is trigonal planar, which can be nonpolar, but since our compound is not symmetric and has 2 lone pairs around oxygen, the compound is polar. For our next problem, number 21, we will be talking about reaction rates. This one asks us to consider the reaction 4pH3 gas yields P4 gas plus 6H2 gas, and if, in a certain experiment over a specific time period, 0.0048 moles of pH3 is consumed in a 2.0 liter container each second of reaction, what are the rates of production of P4 and H2 in this experiment? So we can set up each equation for the rates of P4 and H2 by writing our given 0.0048 moles of pH3 over 2 liters multiplied by the coefficient or number of each element over 4 moles, since that is the overall total of pH3 in the reaction. For P4, we have 0.0048 moles over 2 liters times 1 P4 over 4 moles, and for H2, we have 0.0048 moles over 2 liters again times 6H2 over 4 moles. The rate production of P4 is, in scientific notation, 6 times 10 to the negative 4th molarity per second, and for H2, the rate is 3.6 times 10 to the negative 3 molarity per second. The units are molarity per second because the reaction is a zero-order rate, since there is only one 4pH3 in the entire reaction, and it is the only reactant.